Hello BC Calculus students, this is Mr. Johnson and we are continuing our work with section 8.3 and we're going to study the 7th convergence test. I know you probably are thinking to yourself, how can there be more tests to do for convergence? But there are 10 and so we are on now the 7th one. This is basically a piggyback on the 6th test. The 6th test was the comparison test. This is called the limit comparison test. And it is very, very similar. You are comparing two different series. Just like with the comparison test, you're going to pick a series that you know, and you will compare it with the one that you don't know. And in this case, we're going to actually use a limit comparison, and so there is a place for this. I'll hopefully convince you of that as we work on this. But here's the convergence test. So it says that you have two different series, A sub n and B sub n, and they have positive terms. Remember, that's a theme that we're dealing with right now. We will deal with more alternating terms coming up in section 8.4. And so it says if the limit, and this is really important, so the limit of A sub n over B sub n is equal to C, and C is a finite number, and C is greater than 0, then either both series converge or both diverge. Now the key to this entire convergence test is that you understand what B sub n is going to do. So B sub n is the one you're going to select, and B sub n will be in the denominator of the comparison that you're going to take the limit of. Okay, so for example, if B sub n converges, and the value you get is a value larger than 0 that is finite, not infinite but finite, then A sub n will also converge. Or if B sub n diverges, then A sub n will also diverge. So it's a nice test to use. All right, here's what we're going to do. We're going to work through the example 6 you see below, and I'm going to try to walk you through the reasoning behind the use of this test. Now, the important and the really challenging thing here, the important thing is that you know when when to use this test and which other tests are going to be used prior to it. For example, in letter A, you could sort of go a little bit crazy by trying to use the limit comparison test on this particular one because it's not going to work. This one is simply test number 1. It's the limit as n goes to infinity of 3n over n plus 2, and that limit is 3, which is not equal to 0. Therefore, this is divergent by the nth term test, or the limit test, or the test for divergence, whatever name you would like to use. They all sort of mean the same thing. So that's convergence test number 1. Okay, the remaining parts of this problem, B, C, D, and E, are all very, very similar. Now here are some characteristics that I would at least suggest you think about. With the limit comparison test, we're going to want to look for a series that has a rational component. Now that's not 100% of the case. Okay, I'm going to show you an example in a little bit where it's not rational. But a rational series is going to have a polynomial divided by a polynomial. And our goal, if you think through the fraction you're dealing with here, if we have a rational fraction, we really want to have the same degree polynomial on the numerator as we do the denominator. Because if that is the case, then we're able to take the limit quickly and get a finite number. Okay? So what I mean by that is, let's say we're looking at part B, and we're trying to determine whether or not we need to use the limit comparison test. So I'm looking, and I'm not going to write down all of these because I don't even have enough space, but I'm just going to look at B, okay? If I take the limit of that as it stands, I get a limit of 0 as n goes to infinity. So test number 1 is not going to work. The geometric series test is not going to work because it's not in the geometric form. A collapsing sum is not going to work because the denominator is not factorable. The 4th test is our integral test, and our integral of that is going to be a difficult one. I'm trying to think if it would be even possible. I mean, you may be able to get that to work. I don't really want to, though. It's going to be really difficult because, I mean, we could possibly use a U substitution on that. P series, it's close, but there's too much there. The 3n and the plus 2, those are in the way, so P series is a problem. Okay, now we come to the comparison test. Now the question is, what would we compare this to? Because I think this is maybe the largest challenge when it comes to working with the limit comparison versus the comparison test. So for example, if I take, I'm just kind of brainstorming here, if I take the 2 out of the mix, because the 2 is really sort of the extra issue there. So if we look at, for example, this relationship, the fraction on the left is going to be smaller than the one on the right because you're dividing by more. Now, what is this one actually doing? Well, this is really just 3 divided by n, if we were to simplify that. And this as a series is going to be the harmonic series. I know we're multiplied by 3, that's not a big deal. Or the p series, because p is equal to 1. And so this is going to be divergent. Now, if that is divergent, which it is, if this is divergent and it's larger than that one, we know nothing about that one. It's really important to understand that. This being divergent just basically means this goes off to La La Land, and this one, we have no idea what it does. It could converge, it could diverge, we don't know. Okay, so the comparison test is not working well for us. All right, let's go about the limit comparison test. Now, again, the challenge here is what do you use? Just like the challenge with the comparison test, what do you use as your known series? So we have 3n divided by n squared plus 2. That's our numerator. And we're trying to divide it by something that we know. Now, remember what I said. You want to somehow set up a fraction where your degree in the numerator is the same in the denominator, so you can actually take a limit and get a finite number. And if you think through your options, you want to try to make this a second degree polynomial divided by a second degree polynomial. And the easiest way to do that is to compare it to 1 over n, because algebraically, we get 3n squared over n squared plus 2 if we were to combine this into one fraction. If we were to, make this complex fraction just a single fraction. And notice that our limit is 3, which is greater than 0. Now, the limit comparison test says that if that is the case, both series behave the same way. In other words, the series as n goes from 1 to infinity of 1 over n is divergent. And let's just claim by the p series, we could do the harmonic as well. Therefore, the series from 1 to infinity of our unknown, this is 3n over n squared plus 2, is also divergent. And that would be by the limit comparison test. Okay, all of that work, and basically we are at the point where we have crossed off A and we have crossed off B because both diverge. Now, if we were to take a look at C, I'm not going to do this too much more here, but I just want you to think through this. What's the difference between B and C? Well, we've added this n right here, okay? Is that going to impact us? Well, if we were to take a look at, we could go through the whole conversation I had with you about letter B, test number 1, test number 2, test number 3, and so on. We really get down to the limit comparison again. And in this case, we would end up dividing probably by the same thing, because what we care about is the degree of the numerator and denominator. And if you notice, you end up getting really the same type of situation. Yes, there's a 2n, but we don't really care too much. That limit is going to be 3. We're really going to come across sort of the same analysis that we did in part B. You can work through that. So the series 1 over n is divergent, therefore the one we're looking at is divergent. We can cross off C, that's divergent. Now, I'm not going to do part D because I want you to think about how you're looking for, in this case, you have a second degree and a third degree polynomial, top and bottom. And with this situation, we would have the exact same limit comparison test situation where we're looking at the harmonic series comparison and it's divergent. D will also diverge for really the same reasons or similar reasons that B and C did. Now let's take a look at letter E, and the big difference here with E is that the degree of separation here is 2, not 1, and it was 1 before. So let's take a look at the limit as n goes to infinity of 3n squared over n to the fourth plus 2n. Now we're going to compare this to 1 over n squared, because remember, I want that degree to be the same so that my limit has some sort of meaning here. And I get 3n to the fourth over n to the fourth plus 2n, and my limit is 3, and it's greater than 0. Okay, big deal. Well, remember, we used 1 over n squared, which is convergent now by the p-series test. And therefore, our series from 1 to infinity of 3n squared over n to the fourth plus 2n is convergent by the limit comparison test. Oops. So E is our answer finally. I hope that made some sense, but that's a problem that can certainly take extensive time as you look at each of the options. All right, let's take a look at example 7. So example 7 is one of the ones that I referenced earlier, where you may not have a rational expression, a polynomial divided by a polynomial. In this case, we do not. We have 2 to the n, and so we're looking through, okay, what is the limit as n goes to infinity? It's going to be 0, so test number 1 fails. Is it geometric? Well, here's the thing, it's very close to geometric because this little element of 2 to the n is certainly geometric. The problem is the minus 1 is an issue. So it's not geometric, but very close. It's certainly not collapsing. We cannot factor the denominator. It is not the integral test, because I do not want to take the integral of that. What's our next one? P-series. It is not a P-series. It's kind of the opposite of P-series. The n is in the exponent rather than the base. The comparison test, okay, well let's think about that, because I think that's currently our biggest challenge is, do we use the comparison test for something like this? I think we would probably all agree that this would be most likely the no-brainer in terms of what to compare it to. The minus 1 is sort of the extra element. Now on the left, you're dividing by less, which means that is larger than on the right. Now this one is the one that we know. That is the series 1 over 2 to the n, which is convergent by the geometric series test, because r is equal to 1/2. And so the question is, if this is convergent, does it make this convergent? Well, the answer is not necessarily, because look, it's less than. So if it's less than and it converges, the one that's larger than it could either converge or diverge. It is not a guarantee either way. So the true comparison, the direct comparison test, is not very helpful here. That is not something that we're going to have to rely on. We're going to have to look at the limit comparison test. So we have the limit as n goes to infinity of 1 over 2 to the n minus 1. And the big question is, what do we compare it to? Well, remember, I just compared it to 1 over 2 to the n, and it seemed kind of close, although it didn't quite help us with the direct comparison test. With the limit comparison test, however, we're able to simplify this fraction and it gives us 2 to the n over 2 to the n minus 1. And again, the minus 1 is relatively obsolete here. We're going to get a relationship of 2 to the n over 2 to the n, which has a limit of just simply 1. And that's, of course, greater than 0. And so what we can say is that since the series from 1 to infinity of 1 over 2 to the n is geometric and convergent, then the series from 1 to infinity of 1 over 2 to the n minus 1 is convergent by the limit comparison test. So I hope that makes some sense. That's just an example of how, you might not have, compared to that, the problem above with the rational function where we're looking at the degree of the polynomials, this one's a little bit of a twist on that, and we're obviously utilizing test number 2, the geometric series test, in order to pair it with the limit comparison test. Okay, let's go on to the next page. Okay, example 8. I know it says number 10 there, but that's from back in 2016. So we have the question, which of the following series can be used with the limit comparison test to determine whether the series converges or diverges? So be careful, you're being tested on the concept of the limit comparison test here. It has to be utilized with the test in order to determine convergence or divergence. So let's go ahead and look at, let's just think back 2 examples ago. I had mentioned that when you're looking at a rational expression like this, we're really looking at trying to force that degree of the numerator and denominator to be the same. And so you want to divide by something that will cause that to be true, and letter A will certainly do that. Letter A, if we were to take the limit as n goes to infinity of n squared over n cubed plus 1 divided by 1 over n, will give us the limit as n goes to infinity of n cubed over n cubed plus 1, and that's 1, which is greater than 0. So both of these will diverge because the one we're comparing it to is the harmonic. But let me show you why one of the other ones won't work. So let me just take letter B. So if we were to take letter B and we looked at the unknown series and we divide by 1 over n cubed, we get the limit as n goes to infinity of n to the 5th power divided by n cubed plus 1, and that will be infinite. And so we don't get a finite value greater than 0, and so we're unable to compare it, for example, to letter B. You'll see similar issues with C and D. You'll either get this infinite limit or you'll get a limit of 0. And it needs to be a limit that is greater than 0 but finite. Okay? All right, let's look at example 9. It says, which of the following series, and the key here is that it cannot be shown to converge using the limit comparison test with the series 1 over n squared. I find this problem challenging, just partially the wording, but also there's some really difficult math in here. So for example, with the first problem, we have 4 over 3n squared minus n divided by 1 over n squared. So that's going to give us the limit as n goes to infinity of 4n squared over 3n squared minus n. That's 4/3. That's, of course, greater than 0. And so since the original, let me just write this down. So this is convergent by the p-series test. So because that's convergent by the p-series test, because we got a value that is finite greater than 0, A would also converge. A would be okay to utilize the limit comparison test. So that's not what we're looking for. We're looking at the cannot. So we're looking at the one that doesn't work. Okay, for part B, let's see here. Let's do the limit as n goes to infinity. I'm going to save us a little bit of time on notation. So if we were to take the unknown divided by 1 over n squared, we're going to get 15 n squared over the square root of n to the 4th plus 5. You could utilize some different techniques algebraically to analyze this limit. Ultimately what we're doing, and I guess maybe let me show you this way. The traditional collegiate method of showing this is to divide every one of these terms by n squared. Now under the radical, you're divided by n to the 4th because it would be the equivalent algebraically. And we did all this stuff back in chapter 2, so I know this seems a little bit fast as we speak, but we did this in chapter 2. So you have the square root of 1 plus, hold on, back up. I did like that entire thing wrong. Sorry, I did not divide this by n squared. Okay, so we divide everything by n squared. Inside here, n to the 4th. It's the risk of talking and writing. All right, so we have 15 over the square root of 1 plus 5 over n squared. All right, so what we get here, if n goes to infinity, 5 over n squared is going to go to 0, and so we end up getting 15. That's greater than 0, therefore they both converge. This is gone. That's also going to work. It's not very easy to show necessarily. It's a hard limit to take. That's going to work. Okay, this next one I find pretty difficult because we actually have to use L'Hopital's rule. So we have sine of 1 over n squared over 1 over n squared. The numerator as n goes to 0 will be sine of 0, which is 0, and the denominator will be 0. So this is a L'Hopital candidate. I'm not going to go through all the notation right now. I'm just going to put an L just as a really informal way of saying I'm going to take L'Hopital's really quick. So I have cosine of 1 over n squared times, because of the chain rule, negative 2 over n cubed, divided by negative 2 over n cubed if I'm doing the derivative of the top, then the derivative of the bottom. We can cancel, and cosine of 1 over n squared as n goes to infinity is going to be cosine of 0, which is going to be 1. That ends up also working. Now again, that's very difficult because we're going through, the first one is pretty simple. B and C are both relatively difficult limits. Okay, we're down to D. Obviously this is our answer, and hopefully we would, think through like, all right, let's just do part D first. Maybe we can get a sense that that's going to be the answer early on. But we're taking this divided by 1 over n squared. You end up simplifying this to the limit of the natural log of n, and that is going to be infinite, and so therefore that's going to be our answer. We cannot use the particular one to show convergence of letter D. All right, that's going to be it for this particular video. The last video of this section, we'll just work through the remaining examples as practice. Thank you.